Hi, my name is Jonathan, and welcome to the next section of Cisco SD-WAN. We're talking about working with NAT, network address translation, when we've got a vEdge device. Basically, we have a C-Edge and vEdge device. We're going to talk about the challenges we may run into if they are in different NAT situations. Okay. So, as we're going to talk about NAT, in the next section, we're going to talk about zero-touch provisioning and configuration templates, and then we're talking about redundancy later in this section. All right. And we're going to talk about the challenges that we have with NAT. And as you can guess, there's always some challenges with NAT because there's a different IP address that the device is using versus what it's presenting itself as versus what everybody else is seeing it as, and the two can get confusing. So we need some method of controlling that and understanding what's occurring so that we can make sure that connectivity is maintained. Okay? So first off, the 5-second overview of network address translation. NAT saved the internet. It made it basically extended the life of IP version 4 by 25 years so far and counting. Because everybody doesn't need a public IP address to connect to the internet, we can use a network address translation and hide behind use a private IP address and hide behind one IP address in the front. This is awesome. It's amazing for keeping the internet running. The downside is it creates certain issues for devices that need to communicate to each other via NAT. Okay. We're going to talk about a couple of different NAT types in the next couple of slides, and versus full cone NAT versus address restricted cone versus port restricted versus symmetric NAT, and we'll talk about stun as well. And stun is actually pretty cool. It's a method of traversing NAT for certain UDP protocols. All right, and that also adds a firewall function because I'm not exposing my own personal reachability to everyone else on the internet. Because I have a private IP address, you can get to the public IP address, but after that, routing to me gets very difficult for you. Okay? So, by default, all SD-WAN devices are going to use base port 12346 for establishing connections that handle the control and data traffic in the overlay network. Each device uses this port when establishing connections with other SD-WAN devices. We also do a port offset. When multiple SD-WAN devices are installed behind a single NAT device, we configure different port numbers for each device so that the NAT can properly identify each individual device. So if I have, let's say, 5 SD-WAN devices behind one IP address, each one will have an offset IP port mapping so that they're not all appearing as the same 5-tuple to the world. That IP address, protocol, and port. If it's the same, then there's no way for me to map an outside to an inside. Okay? The default port offset is 0, so for the first device, it's going to be port 12346, and then we go up from there. In the context of the SD-WAN overlay network, port hopping is the process in which devices try different ports when attempting to establish connections with each other if a connection attempt on the first port fails. So after each failure, the port value is incremented and the connection attempt is retried. The software rotates through a total of 5 base ports, waiting longer between each connection attempt. Of course, I said before, the default base port is 12346, this guy down here. Okay. Port hopping is done sequentially among ports 12346, 12366, 12386, 12406, and 12426. And then returns back to 12346. So if we've timed out on all of these, we're going to go back and start over. And we use this when attempting to establish those connections to vManage, vBond, and vSmart. We can also manually request a vEdge router to port hop. Typically, port hopping is not required and does not occur on these devices on the vSmart controllers, vManage, etc. This is generally going to be something that we really do for vEdge. Also, these are the ports you're going to need to allow outbound. If you block your outbound control connections, we need to allow all of these UDP ports outbound. I know a lot of PCI compliant companies are currently blocking outbound connections unless there's a business case. Well, lucky. We now have a business case to allow these UDP ports outbound on your network. Okay, so we mentioned a couple of different types of NAT. The first one I want to talk about is something called full cone NAT. It's also one-to-one NAT, which means we map an internal address and a port pair with an external address and port. Any external host can send packets to LAN devices behind the vEdge router by addressing them to that external address and port, right? So I may be IP address 192.168.1.1. I am a one-to-one, so we're basically equal to that IP. Whoops, let me cross that out. We have a public IP address for that other device, right? So we have a straight connection to it. We don't need to try to invent and worry about NAT. The other one is address-restricted cone NAT. It's also another method. It maps an internal address and port to an external address and port. However, an external host can send packets to the internal device only if the external address has received a packet from the internal address and port first. So, like if you're familiar with an ASA and a stateful firewall, when we allow outbound connections, but we also allow the return traffic, if it's been initiated from the inside, this is the same thing, right? If the outside tried to get in without being first contacted by the inside, it would be blocked. But if the inside started first, then the outside can get back in on the return. We're basically looking for that established on the return traffic. And then we have port restricted cone NAT. This is basically a stricter version of the restricted cone NAT, in which an external host can send packets to the internal address only if the external address and port have received a packet from the internal port first. And the external device must send packets from the specific port to the specific internal port. Okay? It's similar to the address restricted cone NAT, but the restriction includes port numbers as well. We also have symmetric NAT. Each request from the same internal IP address and port to a specific destination IP address and port is mapped to a unique external source IP address and port. If the same internal host sends a packet with the same source address and port but to a different destination, the NAT device creates a different mapping. Only an external host that receives a packet from an internal host can send a packet back. vEdge routers support symmetric NAT only on one side of the WAN tunnel. That is, when a vEdge router operates behind a NAT device running symmetric NAT, only one NAT device at either end of the tunnel can use symmetric NAT. The vEdge router that is behind a symmetric NAT cannot establish the BFD tunnel, that's bidirectional forwarding detection, with a remote vEdge router that is behind a symmetric NAT, an address-restricted NAT, or a port-restricted NAT. All right, all that sounded like it really complicated of who could talk to who. We have a chart, okay? So, as expected, if both sides have public IP addresses, we're good to go, okay? Full cone to full cone, that means this is basically each of these present themselves as a public IP address out. We're also good to go. And you'll note that we've got this little matrix here. Full cone can talk to basically anybody, all right? Port address restricted can talk to port address restricted only. Public can talk to symmetric, and symmetric, of course, can't talk to symmetric, and symmetric can't talk to port address restricted. Okay? If you're set up like this and you only have devices behind NAT and everybody's behind NAT and they're all like using an overload or something, your solution is going to generally be to place a vBond or a vSmart inside your environment so that the private connections can reach it. Okay? By default, here's the thing. You're going to have devices with internet connections. If you've got a site that only has private connections and we only have cloud servers, we're going to have a problem getting that site connected to the SD-WAN solution. Generally, what we're going to want to see is every device to have a public IP address of some sort, either via a cable modem or a DSL line or a 4G connection. But remember, a lot of those connections, especially DSL and 4G, assign private addresses to those devices. So you're probably going to need some business level of DSL or those so that you can get public IP addresses on those devices. The best case scenario is always going to be having on this top row, having public IP addresses on every single one of the devices. But we understand that that's not possible. That's why we have other options here. Okay. Let's take a closer look at how this NAT detection is going to work in the SD-WAN solution. So vEdge routers always reach out first to the vBond orchestrator at startup. It automatically detects whether there is a NAT function in the path. So this vBond orchestrator is going to act as this stun server, that session traversal of UDP through NAT. And the vBond orchestrator receives a packet where the vEdge router puts its own address and source port into the payload. It compares the external IP and port to the IP and port inside the payload and determines a NAT function. All right? This is a fancy way of saying you sent me a private IP address and port, but it came from a public IP address and port, therefore you're behind NAT. Okay? So once that happens, the vBond orchestrator informs the vEdge routers about how that NAT is set up. And the vEdge router communicates the translated address to the vSmart controller. The vSmart controllers announce the public address to other vEdge routers so they can communicate. In the example here, vEdge 1 uses IP1, which gets translated to IP1 prime. Okay? So when vEdge 2 sees it, this is what he sees. That's that public IP address through the system. Okay? The vBond orchestrator detects the translated address, informs the vSmart controller, and vSmart sends IP1 prime to the peer vEdge router. That way both vEdge routers know which address to use, and NAT can be traversed without a problem. Of course, this is assuming full cone NAT, right? Remember, both of these have static mappings, one-to-one mappings from their private IP addresses to their public, right? Allowing those UDP ports that we talked about earlier, the 1, 2, 3, 4, 6, etc. Okay? This works fine, right? Because both sides have static public IP addresses that they're pointed to, even though they have private IP addresses assigned to them. Now, if we have full cone and symmetric, if one side is using symmetric, okay, we're only going to accept inbound connections after it has initiated an outbound connection to the same destination. So in the example on the slide, vEdge 1 router initially can't send a packet to the vEdge 2 router because from the perspective of vEdge 2, it does not have an outbound connection yet. Hence this little X. Okay? Remember, symmetric is expecting to only a receiving packet only if it is sent one first. Okay? So if I block this because I'm only allowing in established connections. However, when the vEdge 2 is behind symmetric NAT, the connection succeeds. We reach out, so our vSmart and vBond know that vEdge 2 is behind a symmetric NAT, so we're going to tell vEdge 2 to initiate the connection. And since he initiates the connection, the return traffic is now allowed. Okay? And this is why that'll work. So, this summary page here talks about zero-touch provisioning, which we're going to discuss in the next slide deck. But generally, though, we do operate over most NAT deployments. And for special cases, you can configure settings to facilitate NAT traversal. So give us a moment. We'll talk about ZTP in the next sessions. Thank you very much.